Hi everyone, welcome to today's lesson. Today we're going to be looking at derivatives of trigonometric functions. And as you can see on screen, what I have produced here is two different functions. The first function is f of x is equal to sine of x all divided by x. And that's a function on the left, which is denoted in the color green. And I also have a different function on the right hand side of the screen, which is denoted as g of x. That's my blue function, which is the quantity of cosine of x minus 1 all divided by x. And the reason I wanted to show you these specific graphs here is because from the initial graphs we can then start extracting this particular concept. That if we're looking at the limits as x is approaching 0 for f of x, where f of x in this case is going to be sine of x divided by x, well, from the graph we can see that the value of the function does not exist at x is equal to 0. However, identifying that we are working with limits, it doesn't matter whether the function value exists or not. What we're looking for is, does the limit as x is approaching 0 for that function exist? And as we're traveling from the left hand side on that function and from the right hand side of that function as we're approaching 0, then we're naturally converging on this point, which is going to be a y value of 1. So when we're looking at sine of x divided by x, again, we must interpret that that function might not exist at x is equal to 0, but we do get the limit to be evaluated. The other limit on the second graph, well, for that one, if we look at the limit as x is approaching 0, once again, for that function of cosine of x minus 1 all divided by x, then this limit as we're approaching 0 on this function, that limit will also evaluate to be 0. Which means at this point in time, we can then really say that both of these limits do exist for these functions as x is approaching 0. And we must have these in our minds at all times when we're working with any type of calculus. So I want you to make sure to have these in your mind at all times. Okay, so those are the limits that we need. And I'm actually going to box this. There we are. There we are. Perfect. So what we want to do now is we want to start investigating this derivatives or these derivatives of trigonometric functions. So what we're going to do really quickly is we're going to derive what the derivative for cosine of x should be. Okay? So I'm going to say here, let f of x be equal to cosine of x. And now we want to investigate f prime. F prime, or as we like to call it, the derivative of x, by the limit definition will be the limit as h is approaching 0 for my function f of x plus h minus f of x all divided by h. And again, I'm just using that limit definition that we developed in the previous sections. And I'm going to make my substitutions at this point in time. So the limit as h is approaching 0, my function is cosine, which means I will have cosine of x plus h minus my function value, which is just cosine of x, as such. All of this is divided by h. Now, again, we can't take the limit here directly because, again, we're going to be left with an indeterminate form. However, we can use a few properties to simplify this as we continue to work through. And one of the first properties that I'm going to be using here is going to be that cosine of x plus h, in other words, the sum of two angles for cosine, this is going to be cosine of x times cosine of h minus sine of x times sine of h. And again, this goes back into the sum and difference formulas for your addition or subtraction of trigonometric angles for sine and cosine. All right, so once we're able to extract this, I'm going to go back to my limit, and we're going to say the limit as h is approaching 0. And now I have to put in this big piece. All right, let's make sure we get a good fraction bar here. Oops, my apologies there. There we are. Let's get a big fraction bar here. All right, if we don't need the rest, we'll eliminate that. Okay, so here what I'm going to have is going to be cosine of x times cosine of h minus sine of x times sine of h, and that's all minus cosine of x. All this is still divided by h. And again, this cosine of x plus h, let's change the quality, or there we go. There we are. And so now what we're going to do is we're going to try to see if we can, let's say, simplify, or if we can factor something out. That way we can make sure that we try to work our best with what it is that we're looking at. So one of the things that I want to do is I see a cosine of x on one term, and I see another cosine of x as another term on that numerator. And so what I want to do is I want to group them together. And when I group them together, my hope is going to be that I factor something out. Here we go. Because if I can factor something out, then that gives me something to work with. Okay, so again, I'm just going to commute my terms together, or associate my terms. There we go, minus cosine of x minus sine of x times sine of h, all divided by h. Okay, so again, I just commuted that term. Now I'm going to factor out the same term, cosine of x. So let's go ahead and get that started. Whoops. All right, so again, for the first two terms, we're going to factor out cosine of x. What remains is cosine of h minus 1. There we are. And then we have minus sine of x times sine of h. And this is all divided by h. So again, all I did was I factored out the term out of the first two terms. And I'll make sure I highlight that here. Let's highlight this in yellow. Here's cosine of x, here's cosine of x, and there's my factor. All right. Now, what we're going to do is we're going to now distribute this limit into each individual component, or into each individual term on that numerator, while simultaneously deconstructing this fraction into its appropriate fractions where they all have a divisor of h. So what happens here is that we then take the limit as h is approaching 0, and we're going to have cosine of x multiplied by, and here goes my fraction, multiplied by cosine of h minus 1 divided by h, That's the first term under the same divisor, or sorry, with the same divisor. There we are. And again, I'm distributing that limit, so minus the limit as h is approaching 0, and in this case I have sine of x. Oops. So in this case I have sine of x multiplied by sine of h. Okay, it's not looking too bad. There we are. Now we can go through and we can keep taking the product of limits. So taking the product of limits, what you're going to see here is that the limit, so I'm going to outline this, that, let's do this in a different color. Let's do this in orange. The limit as h is approaching 0 for cosine of x, notice cosine of x, this function does not depend at all on this h value that is tending to 0. Therefore, cosine of x is a constant when we're taking the limit as h is approaching 0. In other words, this is not affected, cosine of x, which means the limit as h is approaching 0 for cosine of x is simply just cosine of x. Okay, and very similarly, the limit as h is approaching 0 for sine of x, well, again, sine of x does not depend on h because it has no h representation embedded in the function. Therefore, the limit as h is approaching 0 for sine of x, we're just left with sine of x. So let's go ahead and let's finish off this limit calculation here. So again, the limit as h is approaching 0 for cosine of x, well, that's just cosine of x. Now we have this limit in the bracket, which is a limit as h is approaching 0 for cosine of h minus 1 all divided by h, minus the limit for sine of x. Well, remember, limit as h is approaching 0 for sine of x is just sine of x. However, we do have sine of h, and that's going to be the limit, so let's multiply that out. That's going to be the limit as h is approaching 0 for sine of h. Now we can keep going. Now look at the first limit that is embedded here. Okay, so you know what, before I carry on, I'm going to highlight what I did here. Cosine of x, that was my limit for cosine of x, and sine of x, well, that was my limit that came out here. That was this big piece and this big piece. There we are. Okay, so look at the first limit in the brackets. Limit as h is approaching 0 for cosine of h minus 1 all divided by h. That looks very, very familiar. So look at the top of your screen. Well, the top of a screen tells me that at this point in time, what I'm looking at for the limit as cosine of x is going to be, oops, you know what? Yes, is going to be 0. Now, I just realized I made a mistake here, and gosh, oh gosh. Gosh, oh gosh, oh gosh. Okay, here we go. My mistake was when I forgot to distribute the denominator of h to that second function. Oh, good golly. Sine of h divided by h. There we go. So then we still have sine of h all divided by h. There we go. Perfect. Now it's all fixed. So my first limit, this is going to evaluate to 0, which means we're going to have cosine of x multiplied by 0 minus sine of x multiplied by this limit. And again, that limit looks highly familiar. Looking at the top left of your screen, we have the limit as x is approaching 0 for sine of x divided by x is equal to 1, which is this exact same interpretation. So we get negative sine of x multiplied by 1. once everything settles, we're now left with the answer of negative sine of x. And remember, this signified that we were taking the derivative of my function, and my function was cosine. Therefore, what we can extract is that when we take the derivative of cosine of x, that derivative is going to be negative sine of x. And again, that's using our limit laws for derivatives. And so we want to make sure that we keep on extracting these for all of the different trigonometric functions. So we now want to find the derivative of sine, the derivative of tangent, derivative of cosecant, secant, and cotangent. That way we can build a big list of these derivatives of trigonometric functions. All right, so I'm going to write those functions out, and then we'll come back and we'll start reviewing them. All right, so here are your derivatives of trigonometric functions. We have that the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine x. The derivative of tangent of x is secant squared x. The derivative of cosecant of x is negative cosecant x multiplied by cotangent of x. The derivative of secant of x is secant of x times tangent of x. And the last one is the derivative of cotangent of x is negative cosecant squared of x. So again, we must have these derivatives of trigonometric functions memorized as we continue throughout our calculus courses. So again, in my course, you have to have these in your mind at all times when taking derivatives. And so we now want to go into an example that's going to start exploring these derivatives. So we want to now differentiate the following. Part A, we're going to be working with f of x is equal to x times cosine of x plus 2 times tangent of x. And again, when we apply the derivative, we're going to apply the derivative, and again, I'm going to do this step by step. The derivative with respect to the variable that we're working with, in this case it's x. So the derivative of the function f of x with respect to x. On the right hand side, again, we're going to take the derivative of this first term, which is going to be x times cosine of x, plus 2 times this derivative, and again 2 is going to be a constant, and we're going to take the derivative of tangent of x as such. Now for the first term, we're going to need a product rule because we're taking a derivative and we have a function that is multiplying another function. So product rule there. So this now turns into y prime is equal to, well, if I'm going to need a product rule, I'm going to go with that. I'm going to say my u is going to be x, and therefore my du, or in this case u prime, is just going to be 1. My v is going to be cosine of x, and the derivative of cosine of x, in other words v prime, is going to be negative sine of x. Okay, so now to take this derivative, we're going to go through and we're going to use that derivative product rule. And as we use a product rule, again, we're going to start identifying which one's u, which one's u prime, which one's v prime. And so taking this whole process now, okay, so derivative of the first function, that's going to be 1 multiplied by the second function, which is cosine of x, plus the first function, which is x, multiplied by the derivative of the second function, which is negative sine of x. Alright, so that was that first product rule. And then plus 2 times the derivative of tangent. Okay, so derivative of tangent, as we can see from above, we get secant squared of x. Now, if we simplify this as much as possible, we get that f prime of x is going to be equal to cosine of x minus x times sine of x plus 2 times secant squared of x. And there we have it. This is the final answer for that derivative. Wow, that's pretty cool. So again, I'm going to highlight this, that we needed the product rule here. And that was the product rule. So I'm going to make sure we write that here, that we used a product rule. Now, the derivative of tangent of x, well, that one was straightforward. That derivative for tangent of x, that was just our secant squared of x. And so, again, we must be able to work with these derivatives of these trig functions. So, great. Let's keep going. I want part B now. So here goes part B, where we have y is equal to sine of theta multiplied by cosine of theta. And again, identifying that we want to take a derivative here, but we have two functions, one of them being sine of theta, the other one being cosine of theta, and they're being multiplied, then what we're going to do is we're going to use a product rule. So again, using that product rule, I'm going to say that u is sine of theta, which means that u prime is going to be cosine of theta. My v is going to be cosine of theta, which means my v prime is going to be negative sine of theta. And using this product rule for y prime, or let's say dy dx, or you know what, in this case dy d theta, because we're taking the derivative of y, that's the function with respect to theta. And so again, using the product rule, we're going to take the derivative of the first function, which was cosine of theta, multiply it by the second function, which is cosine of theta, times the derivative of the second function, or you can say the second function here, which is sine of x, or sorry, sine of theta, multiplied by the derivative of the second function, which is negative sine theta. And as you can see here, your y prime then turns into cosine squared of theta minus sine squared theta. Okay, so again, here we use the product rule. Cool. But look at that last one. Can we simplify? I think we can. That last one simplifies into cosine of 2 theta. We actually used a double angle identity. Double angle identity. If you can use double angle identities, Pythagorean identities, any identities that you developed in trigonometry, you're more than welcome to, and it's encouraged that you do use them. Awesome. So let's go on with one more and see how this is going to play out. Part C. So here for part C, we're going to have y is equal to, and we're going to have this rational function, which is going to be in the denominator, we're going to have 1 plus tangent of t. In the numerator, we're just going to have sine of t. And actually, I want to put these in. There we go. Perfect. So taking this derivative here, again, we're going to identify that we do have this rational function, or in other words, we have this quotient. And in order to take this derivative, we're going to need to use the quotient rule. So in order to use a quotient rule, I'm going to do the exact same thing that I was doing before. I'm going to identify my u. In this case, my u is my numerator, so that's going to be sine of t. That means that u prime is going to be cosine of t. V is going to be my denominator, which is 1 plus tangent of t, which means that v prime is going to be secant squared of t. So now that I have this, I can go through my function over here and say, well, if I'm taking my derivative for the function y with respect to t, then that's going to involve me using that quotient rule. So I'm going to need a numerator, and I'm going to put this as a big numerator here. Okay, so I'm going to have a function multiplied up top times a function at the bottom times another derivative and another function. So let's find out what those functions are. Alright, so derivative of top, that's cosine of t, times the bottom function, which is 1 plus tangent of t, minus the top function, which is sine of t, times the derivative of the bottom function, which is secant squared t, divided by the bottom function squared. Just like this. So we're going to go through and we're going to simplify as much as we can when we distribute here. So let's go on with those calculations here. So again, now I'm looking at y prime. So looking at y prime, I'm going to distribute my cosine. Alright, so let's distribute that cosine. I get cosine of t plus tangent times cosine. Remember, tangent is sine over cosine, so when sine over cosine multiplies cosine, we're just left with sine of t minus, and now we're going to be left with sine of t multiplied by secant squared. And on the right hand side, I'm going to work this out really quick. Sine of t multiplied by secant is 1 over cosine squared of t. Okay, so that looks kind of nice. Where here, I can actually separate this just a little bit to say sine over cosine, that's going to be tangent. Sine over cosine t multiplied by 1 over cosine of t, and therefore we're going to get tangent of t multiplied by secant of t. And so that's what I want to leave in my numerator. Tangent of t multiplied by secant of t. And in the denominator we still have that 1 plus tangent of t quantity squared. There we are. And we can't simplify anymore, so at this point in time, we're done taking that derivative. We can't combine any like terms, we can't simplify any more trigonometric functions, which means, again, at this point in time, that's pretty much it. Great. So let's keep going and let's try to find some equations for tangent lines now when we're working with these different trigonometric functions. Okay, so here's your question. It says find an equation of the tangent line to the curve y is equal to the quantity of 1 plus x multiplied by cosine of x at the point 0, 1. And again, what we're doing here is we want to find the equation of the tangent line. So finding that equation of the tangent line, again, is going to imply that we need a derivative. That way we can find the slope of the tangent line at the given value for x for that function. So we're going to start off by taking the derivative. And you're going to see that when we want to take this derivative, we have two different functions. So when I want to work with dy dx, this is going to be a product rule where u is 1 plus x, u prime is 1, v is cosine of x, v prime is negative sine of x. In other words, once you take the derivative of v. So what I have here is going to be the derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second. Okay, so derivative of the first multiplied by the second function. Then we're going to go with the first function, 1 plus x, times the derivative of the second, which is negative sine of x. Let's clean this up a little bit more. And so far we have that y prime, let's make that prime, there we go, is equal to cosine of x, let's distribute, minus sine of x minus x times sine of x. And now if we want to find the slope of the tangent line, then what we can do here is we can take the slope of the tangent line. This is going to be y prime evaluated at the given value of x. The given value of x is from the ordered pair, where we're going to have x is equal to 0. So we make our substitutions. Cosine of 0 minus sine at 0 minus 0 times sine at 0. And identifying that sine of 0 is just 0, then naturally this slope of the tangent line then becomes just 1. Well, that's pretty cool, because now we then get to use the point slope form so that we can extract the equation of the line. So y minus y1, again that's from the ordered pair, is equal to m, which is the slope that I found of the tangent, times x minus x1. x1 is 0, which means the equation of the tangent line is just y is equal to x plus 1. And that's it. So again, working with these derivatives and working with the trigonometric derivatives are something that is going to be crucial as we progress through this course. Now let's try a different example, and these examples are going to involve limits, and these limits are going to be from what we saw at the very beginning of this lesson. So we want to find the following limits. Part A, we're going to be working with the limits as x is approaching 0 and this is going to be for sine of 3x times sine of 5x, all divided by x squared. And so when we have these limits where we have these, let's say, trigonometric functions, you're going to see that a direct substitution is going to leave you with 0 over 0. So we can't do direct substitution. So I'm writing a direct substitution. Results in 0 divided by 0, which is indeterminate form. This indeterminate form for us just means that we can't evaluate the function as is. So what we then have to do is we then have to find some sort of either algebraic manipulation or some trigonometric simplification that will allow us to evaluate the limit so that the result will not be indeterminate form. So there's a few options to take here. But one of the most prominent ones that we want is because I see sine in the numerator for 3x and for 5x. What I want then is I want to be on the lookout for the limits as x is approaching 0 for sine of x divided by x, because I know that this limit is equal to 1. So all we have to do then is just kind of match this numerator and denominator. So match the argument with the numerator, match the argument of sine with the argument of the denominator. Okay, so let's go with that. I'm going to be looking at the limit as x is approaching 0. I still have sine of 3x. I still have sine of 5x. But the denominator I'm actually going to split into x times x. Okay, so let me know if you all agree with that. And I'll pretend I heard you all and you said, yes, we agree. Awesome. Now, what we're going to do then, in order to match the denominator with the argument of sine of 3x, I need a 3 in that denominator. But I not only need a 3 in that denominator, I also need a 3 on that numerator. And so what I'm going to do here is I'm going to multiply both numerator and denominator by 3 times 5. Now notice 3 times 5 divided by 3 times 5 is just 1, which means I'm not changing the value of the function, I'm just changing the way it looks. So here we have the limit as x is approaching 0, and now what I'm going to have, my 3 times 5, I would agree that that's 15, so I'm going to keep that here, multiplied by sine of 3x divided by 3x multiplied by sine of 5x divided by 5x. And again, that denominator is still being multiplied. Now, I cannot split my fraction into individual addition or subtractions because we don't have that in the numerator. However, we are taking a limit of a product of functions, which means the limit of a product of functions is going to be the limit or the product of the limits. So sine of 3x divided by 3x multiplied by the limit as x is approaching 0 for sine of 5x divided by 5x. As such. And now we can see here, well, look at the first limit. Now the first limit that we're taking here, this limit, now has that same feel that we were looking at the limit for the top right hand portion of part A. The limit as x is approaching 0 for sine of x divided by x is equal to 1. The second limit also has that exact same feel. We were able to match the numerator argument with the denominator of 3x, which means at this time both of those limits are equal to 1, and we're left with 15 times 1 times 1, which is just 15 as our limit. So check that out. That's actually really cool. Let's try part B. So for part B, we then want to look at this limit, which will be the limit as x is approaching 1 for my numerator. I'm going to have sine of x minus 1, and for my denominator I will have x squared plus x minus 2. There we are. So this is the limit that we then want to take. Now you might be saying, well, we can't do a direct substitution, or you might say, let's try a direct substitution. However, a direct substitution leaves us with indeterminate form. And again, for us, that's bad. That's not good for us. When you get to Calc 2, this will be fun. This will actually be really good for us if we get it in this form. For us, though, because we don't have certain tools at our disposal, we still have to, in a way, drag our feet through the mud because we need to employ the limits and the properties that we're learning at this point in time. So what I want to do is I kind of want to bring this to your attention here, that when we're looking at this particular limit, I do see sine of the numerator. So again, I'm looking at sine for my function. So I want something like this, where I have the limit as x is approaching 0 for sine of x divided by x. I know that limit to be 1. In other words, I want the argument of sine to match that denominator. So if the argument of sine in our example is x minus 1, I want that same argument in the denominator. So let's check to see if we can get that. So the limit as x is approaching 1. Let's see if we can get it here. All right. Denominator, I believe it's factorable. X plus 2 times x minus 1. Numerator stays exactly as is. So now we can see, hey, this kind of does match here. Okay, but we got to do a little bit more work now. Let me see if we can go through and if we can simplify this just a little bit more. Since I have a product of functions here, what I want to do is this. 1 over the quantity of x plus 2 multiplied by sine of x minus 1 divided by the quantity of x minus 1. And if we do this, now we can distribute that limit for these functions. Because we're taking a product of functions and we're evaluating that limit, then we can evaluate the limit of those individual products or those individual functions and then multiply them. Which means we'll be able to evaluate the limit as x is approaching 1 for the quantity of 1 divided by x plus 2. And we're also going to be able to evaluate the limit as x is approaching 1 for the quantity of sine of x minus 1 all divided by x minus 1. Look at that. That is awesome. Okay. So the first product, or that first limit for that product, that one's a direct substitution. That one's not too bad. So that one's just 1 over 3. Okay, that's pretty good. But now let's pay attention to the second one. Well, look at your limit on the top right hand portion for part B. We need to have the limit as x is approaching 0. Okay, well, that's going to be fine. But what I want you to see here is that if we, let's say, make a substitution, let's say that we had something along the lines of u, or you know what, let's call it theta. I like theta. Theta is equal to x minus 1. Okay, if you make this substitution into your function, then you have the limit of theta, or sorry, geez. The limit, we're going to have some stuff down here, so I'll keep that as is. The limit of sine of theta divided by theta. Now, x is going to be approaching 1. So what I'm going to do is I'm going to modify this just a little bit more. Okay, so I'm going to say as x is approaching 1, so these x values keep getting closer and closer to 1. What is that going to make theta? So as x is approaching 1, theta is going to be approaching, well, these values get closer and closer to 1. 1 minus 1 is going to be 0, which means the limit as theta is approaching 0 with this substitution. And check that out. What is that limit? Well, that limit is this one, which is 1. Which means this overall limit that we were looking for is actually 1 by that process. Yay! Which means, what is the overall limit? Well, the overall limit for that function that we were initially given is just 1/3. Check that out. That is awesome. Great. Now, let's work on one more example. Okay, so we're going to work on one example, and we're going to go with this, that we want to find we want to find which derivative here. I think I want to go with a derivative to the 999th power x 999 times for the function of cosine of x. So we're going to have to take this derivative 999 times. So you're going to identify that, yeah, taking the derivative 999 times is not very time effective. In other words, it's very opposite of that, which is time consuming. So what we want to do is we want to kind of find a way to see if we can bypass this. All right. And so recalling that derivatives, or let's say recalling that functions, sine and cosine, are periodic functions. Meaning after a certain amount of period, they just keep on repeating themselves over and over and over. We also saw that derivatives of these trigonometric functions are also going to be periodic. In other words, the derivative of sine of x is cosine of x, the derivative of cosine of x is sine of x, meaning that they kind of cycle back through all of their initial values. And so let's start off a pattern. So I want to say first, establish a pattern. Okay, so let's start establishing a pattern. Let's look at y prime. Okay, so let's look at the first derivative. Let's say y prime. So y prime, or you know what, I'm going to say let y is equal to cosine of x. That way we identify that our y function is cosine. Okay, so y prime is going to be negative sine of x. Let's find y double prime. So the second derivative, that's a derivative of negative sine. Well, that's going to be negative cosine of x. Third derivative, y triple prime. The derivative of cosine is negative sine, but we have a negative, so it's going to be a positive sign. And finally, taking the fourth derivative will get us cosine of x. And if we take the fifth derivative, y to the fifth derivative, or fifth derivative for y, this is going to be back at negative sine of x, which means it starts repeating. If I take the sixth derivative, it'll just repeat to the second derivative. So identifying the pattern here, this is a pattern that we want to identify. And again, this pattern is then going to allow us to generate all of the different derivatives, because all of the different derivatives past the fourth derivative are just going to cycle through one of those beginning options. So this is the pattern. let's actually rewrite that. So it's a pattern. Higher order derivatives cycle through these four derivatives, or through these four functions. So in that instance, now that we found this pattern and that we've identified it, we can now start looking at the different remainders. Okay, so looking at the value for 999, what I want to do is I kind of want to split that remainder into one of these derivatives. Is this derivative for the 999th power going to fall under a remainder 1, a remainder 2, a remainder 3, or a remainder 4, which goes evenly, which means this has no remainder at all. In order to identify this, we then need to start breaking down that power of 99. So what I'm going to do is this. 999 divided by 4. And in order to find this, what we're going to do is we're going to make sure that we, let's say, convert this into an improper fraction, which means 4 goes into 999 249 times, and then we have 3/4 left over. Well, again, 249 and 3/4. This means 4 goes into 999 times, or 999 249 times, with a remainder of 3. Well, then, which remainder then occurs? Well, the first one is remainder 1. So I'm going to identify this here. You know what? Let's just go here. R1, remainder 1, remainder 2, remainder 3, and then no remainder. So anytime that we have a remainder, we then identify where we're at. Since this has a remainder of 3, this is going to tell me that this is my answer. Whoa, look at that. That's crazy. I wonder what happened there. Okay. So here we are. So to answer this question, if we then keep going and take the 999th derivative for those x's 999 times of cosine of x, then the answer here is going to be that remainder of 3, which is going to be just sine of x. And there we are. So we need to identify the pattern. Once we identify the pattern, we just use our conversion of the fraction for 999 divided by 4 to find what is the remainder. Once we have that remainder, we just identify which derivative that falls under. And that's pretty much it. That's all you have. So I hope you all enjoyed this lesson, and I hope to see you all around for the next one. Till then, have a good day.